Welcome physics people. In today's video we're looking at motion. Our topic for today is the equations of constant acceleration, and the skill we're looking at is setting up and solving problems. The equations of constant acceleration are constructed using the following variables. So we have displacement, the shortest path from the start to the finish, and that's measured in meters and has the symbol S. An initial velocity measured in meters per second, and that has the symbol U. A final velocity in meters per second also, it has a symbol V. A, the acceleration, is measured in meters per second, and T, the time, is measured in seconds. A quick visualization. So consider a journey of constant acceleration in the following manner. So acceleration means an object can slow down, it can speed up, or if you like, an acceleration of 0 means it maintains a constant velocity. So here we have our starting position and our finishing position. So at the start, we have an initial velocity. The object might be stationary, it might be traveling at 10 meters per second, whatever the case, that's our initial velocity. Over the duration of this particular journey, and remembering that it is constant acceleration, we have an acceleration rate in meters per second squared. At the end of this particular period of acceleration, we'll get the finish line, and we'll have a final velocity. The object will have traveled some displacement, and will have taken some time t. So let's recap the equations that we have available. The following 5 equations provide us with the tools to calculate unknown SUs, As, Vs, and Ts, what we refer to as suvats. So first of all, our first equation is V equals U plus AT. Our second equation, S equals UT plus a half AT squared. Our third equation, S equals VT minus a half AT squared. Our fourth equation, S equals a half in brackets U plus V, close brackets, times T. And finally, V squared equals U squared plus 2AS. These 5 equations are commonly referred to as the suvat equations, taking the 5 symbols S, U, V, AT. Now, a quick look, please. The very first equation, V equals U plus AT, it contains a V, U, A, and T, and it's missing an S. The second equation, S equals UT plus a half AT squared, it contains an S, a U, an A, and a T, and is missing the variable V. Our third equation, S equals VT minus a half AT squared, it contains the variables S, V, T, and A, and missing a U. Now, if you go through each of these 5 equations, you'll notice each equation varies by one missing variable. Now, typically, you'll be given 3 of these variables and asked to solve or calculate the 4th variable. There's 3 standard steps we'll follow on each of these examples. First is, we'll list down the variables, that is the S, U, V, A, and T. The second is we'll select an equation. And the third is we'll substitute in our values and solve for the unknown. So let's look at the following examples. So example 1. A stationary car drives away from a set of traffic lights at a constant acceleration rate of 5 meters per second squared. What is its final velocity after 10 seconds of acceleration? Now, straight away, we can see there is constant acceleration in the description. So we know we can use our suvat equations. There goes our vehicle from the traffic lights. So we state our variables. The initial velocity is 0 meters per second as the car is stationary. The question we're trying to solve is what is the final velocity? So V equals question mark. S, the displacement, is not given in this example. Okay, there's no mention of displacement in this description. A, the acceleration, is 5 meters per second. And T, the time, is 10 seconds. So there's our variables. Let's now select the equation. We've got 5 different options. Which equation are we going to use based on the variables we have? Only one equation doesn't include an S. So if we look at those 5 equations, we can see that the S is not given. So this second equation can't be used. Third equation can't be used. Neither can the fourth or the fifth, because they all involve the variable S for displacement. In fact, the only option we have is V equals U plus AT. And so that's the equation we'll select. Many students say, which particular equation do I use? And the truth is, there's only ever one equation that works for a given scenario. So let's substitute and solve. Here's our equation, V equals U plus AT. We substitute in our values. So V was the unknown, U was 0, A was 5, and T was 10. So when we have 0 plus 5 lots of 10, we end up with a final velocity of 50 meters per second. Simple setting out, simple calculation. Example number 2. A stationary car drives away from a set of traffic lights at a constant acceleration rate of 5 meters per second. Same initial scenario as example 1. How far will the car have traveled after 10 seconds of acceleration? So there goes our visual. State our variables. Our initial velocity was 0 meters per second. Our final velocity in this case is not given. There are no mentions of the final velocity in the description. Displacement is what we're trying to calculate, how far. The acceleration, It has a constant acceleration rate of 5 meters per second, and again the time is 10 seconds. So let's select the equation for this particular scenario or story. You can see that we have v not being given, and only one equation doesn't include a v. That's right, it's s equals ut plus a half at squared. The other 4 equations of constant acceleration involve the letter or the variable v. So let's substitute in our values for that particular equation and solve. S equals ut plus a half at squared. S is what we're after. It remains a symbol. U was 0, initial velocity of 0. Time was 10. A was 5 meters per second, and the time again was 10. Now, this particular equation, the square is only on the time. That's a common mistake that students make. They take the half times it by 5 times by 10 and then square everything, but the square is only on the 10. So 0 times 10 gives us nothing. 10 squared is 100, times 5 is 500, and then times that by a half gives us a displacement of 250 meters. Example number 3. A car traveling at 20 meters per second sees a stop sign ahead in the distance. If the car decelerates at a rate of 4 meters per second, how long will it take the car to stop? So here's our visual. Car comes in, reaches the stop sign, decelerates. So let's state our variables. Initially, it says that the car is traveling at 20 meters per second. That's the start to our description. Its final velocity is 0. Okay, at the end of the motion description, the car stops. This represents a final velocity of 0 meters per second. The displacement is not given. Okay, there's no mention of displacement or s in the description. Acceleration is negative 4 meters per second. Now this may be a little bit confusing. Our description says decelerates at a rate of 4 meters per second. Now acceleration is when you speed up. Deceleration is when you slow down. So if I decelerate at 4 meters per second, that's the same as accelerating at negative 4 meters per second. And finally, the time is what we're trying to calculate. How long will it take? T equals question mark. Here's our 5 equations. Can you select the appropriate equation? Once again, only one equation doesn't include the variable s for displacement. And it's the top one, v equals u plus at. All the other 4 remaining equations of constant acceleration have the symbol s, or the variable s, in them, and therefore can't be used. So let's substitute our values and solve. V equals u plus at was our chosen equation. The final velocity was 0. The initial velocity was 20. The acceleration, well, it's decelerating, so the acceleration is negative 4 meters per second, and the variable t is our unknown for time. Let's simplify that. 0 equals 20 minus 4t. I'm now going to add my 4t to the left-hand side to simplify it. Now I have a statement that says 4t equals 20. Now to get rid of the 4 times t, I'm going to divide both sides by 4. And that leaves me with an expression, t equals 20 over 4, which means my time is 5 seconds. Example number 4. A car traveling at 20 meters per second sees a stop sign ahead in the distance. If the car decelerates at the rate of 4 meters per second, the same introduction as the previous example 3, how far will the car travel before stopping? So let's state our variables. The initial velocity is 20 meters per second. Final velocity is 0 because it's stopping. How far will the car travel? So s, the displacement, equals question mark. The acceleration, because it's decelerating at 4 meters per second, we state the acceleration is negative 4 meters per second. And of course, in this case, the time is not given. So there's no mention of time in this description. Let's select the correct equation. Now, which equation doesn't use the t equals time? Okay, only one equation doesn't include the variable or letter t. And that is v squared equals u squared plus 2as. So step 3, our final step, substitute and solve. So our equation is v squared equals u squared plus 2as. Let's substitute in our values. So the final velocity was 0. Our initial velocity was 20. Our acceleration, in this case, is negative 4 meters per second, and we want to find the variable s, our displacement. So we leave that as an s. Let's simplify. 0 squared becomes 0, 20 squared becomes 400, and 2 lots of negative 4 give us negative 8 times s. So we now have our statement, 0 equals 400 minus 8s. Now to get the 8s by itself, we're going to add that to the left-hand side. And at the moment I have a new statement, 8s equals 400. To get rid of the 8 lots of s, I'm going to divide both sides by 8, leaving me with s equals 400 divided by 8. So the displacement in this case will be 50 meters. Example number 5. A tourist drops her camera from the top of a bridge to the ground below. The fall takes a total of 1.5 seconds from top to bottom. How high is the bridge above the ground? So let's watch our visual. Oh no, she's dropped the camera. Let's state the variables. Our initial velocity is 0 meters per second. So when an object is free falling, it has an initial velocity of 0. This is not stated in the question, so we have to appreciate that an object falling under gravity towards the Earth has an initial velocity of 0, unless stated otherwise in the description. Now, final velocity is not given. There's no mention of the final velocity v in this description. The displacement, how high is the bridge, how far has it fallen, s equals question mark. That's what we're trying to solve. Acceleration equals 10 meters per second. Now, important that all free-falling objects accelerate towards the Earth at a rate of 10 meters per second. This is a given scenario for any free-falling objects on planet Earth. And note, for simplicity's sake, take the direction of the initial movement as positive. So in this case, the camera is falling downwards, and so we're going to take that as a positive direction. And we'll use that for our direction referencing for our velocities and our displacement and acceleration. The time was 1.5 seconds. We're given that in our description. So select the equation. Which one of these 5 equations doesn't involve the v, because we haven't been given any information about the final velocity? So only one equation doesn't include a v in it. That's right, s equals ut plus a half at squared is the only equation without the variable or letter v in it, so we use that equation. Substitute and solve. So our equation, s equals ut plus a half at squared. Let's substitute in our values. S is our unknown, our initial velocity was 0, our time was 1.5, our acceleration was a positive value of 10, and our time was 1.5. Remembering, of course, it's only the t, the 1.5, that is in fact squared. When I place that in the calculator, I end up with a displacement of 11.25 meters. Example number 6, the same scenario again. A tourist drops a camera from the top of a bridge to the ground below. The fall takes a total of 1.5 seconds from top to bottom. With what speed does the camera strike the ground? Here's our visual again. So let's state our variables. Step 1. Our initial velocity is 0 meters per second. Our final velocity is what we're trying to calculate. Now note, the final velocity when you have a free fall arrangement is often described as the impact velocity. If you like, it's the velocity just the instance before it hits the ground. Students often think when it reaches the ground, it must have a velocity of 0. Now that's a different form of acceleration. That's when the Earth would decelerate the object down to 0. We're using the equations of constant acceleration, and in this case, our constant acceleration is 10 meters per second downwards. So the impact velocity is not 0. It's a value just before the striking of the Earth. So in short, the impact velocity is never 0. The displacement in this case is not given. There is no mention of displacement in this description. And the acceleration, as we stated, for any free-falling object is 10 meters per second. And the time we have is 1.5 seconds. So step 2, select the equation. Let's have a look. We have our 5 equations of constant acceleration. And note that only one of them doesn't include the variable s. So which equation doesn't have an s in it? That's right, it's the top one, v equals u plus at. Third and final step, substitute and solve. So v equals u plus at is our equation. V is the unknown variable or quantity, so we leave that as the v in our equation. The initial was 0. A, the acceleration was 10, positive, and time was 1.5. It's a simple one. 0 plus 10 lots of 1.5 will give me a final velocity of 15 meters per second. That's the impact velocity just before it strikes the ground. Our 7th and final example. A train is initially traveling at 30 meters per second. It takes 20 seconds to accelerate to a final speed of 50 meters per second. What distance would the train have covered during this 20-second period of acceleration? So there goes our train. Step 1, state the variables. So the train is initially traveling at 30 meters per second. It has a final velocity in this description of 50 meters per second. What's the displacement the train would have covered? So s, the displacement equals question mark. In this case, there is no mention of the rate of acceleration in the description, so that's not given. And the time taken is 20 seconds as stated in the description. Let's select the equation. We have our 5 equations of constant acceleration. We are looking for the one equation that does not include the a. So only one equation doesn't include an a. And that, of course, is s equals a half in brackets u plus v close brackets t. So we're going to use that equation. Our third and final step is to substitute and solve. Here's our equation. Let's substitute in our values. S was our unknown. Initial velocity is 30. Our final velocity is 50. And our time was 20. Let's calculate that. 30 plus 50 is 80. Half of that is 40 times 20. Gives me a displacement of 800 meters.
You've been watching a Juddy Productions video. If you've enjoyed and indeed learned something from this video, then please remember to like, share, comment, and subscribe. And as always, thanks for watching.